Good morning, everyone. Thank you for joining me today. I want to talk about something that bothers almost everyone at some point in their lives. Where did all this come from? Look around you. The walls, the floor, the air, the stars outside. Where did it all begin? Most people will tell you confidently that it started with the Big Bang. They say the universe exploded into existence 13.8 billion years ago. They picture some kind of cosmic firework going off in empty space. But here's the problem: that picture is completely wrong. The Big Bang was not an explosion in space. It was not a bomb going off in a dark room. It was something far stranger. And when you understand what it actually was, you realize we haven't even begun to answer the real question. Let me start with what we know for certain. The universe is getting bigger. Right now, as you sit here listening to me, galaxies are moving apart from each other. Space itself is stretching. We discovered this about 100 years ago. Edwin Hubble, an astronomer in California, pointed his telescope at distant galaxies and measured their light. He found something shocking. Almost every galaxy he looked at was moving away from us. The farther away the galaxy, the faster it was receding. At first, this sounds like we're at the center of the universe, like everything is fleeing from us specifically, but that's not what's happening. Imagine you have a balloon with dots painted on it. Each dot is a galaxy. Now inflate the balloon. What happens? Every dot moves away from every other dot. If you're standing on any dot, all the other dots appear to be moving away from you. That's what's happening to the universe. Space itself is expanding. The galaxies aren't flying through space. Space is carrying them apart. Now, if everything is moving apart today, what does that tell you about yesterday? It tells you everything was closer together. Go back far enough and everything must have been in the same place. Squeeze the universe backward in time and it gets smaller, denser, hotter. Keep going. 1 billion years ago, galaxies were closer. 10 billion years ago, even closer. 13 billion years ago, there were no galaxies at all, just hot gas. Keep rewinding. The gas gets hotter and denser. Atoms break apart into electrons and nuclei. Go back further. Even the nuclei break apart into individual protons and neutrons. Further still. Everything becomes a roiling soup of fundamental particles at unimaginable temperatures. This is the Big Bang, not a point exploding in space, but space itself emerging from an extremely hot, extremely dense state. Everything that exists now, all the matter, all the energy, all the space, was compressed into a region smaller than an atom. Then it started expanding, and it's still expanding now. But here's where people get confused. They ask, where did it happen? The answer is everywhere. It didn't happen at a location. Every point in space today was at that initial hot, dense state. Your chair was there. The sun was there. The Andromeda galaxy was there. Everything was there because there was no there yet. Space itself was compressed. Another question people ask is, what did it expand into? The answer is nothing. It didn't expand into anything. Space itself is what's expanding. There's no outside. There's no container. Asking what's beyond the universe is like asking what's north of the North Pole. The question doesn't make sense. Now let me show you the evidence that this actually happened. First, we have the expansion I already mentioned, galaxies moving apart. That alone tells us the universe was smaller in the past, but we have much better evidence. In the 1960s, two scientists named Arnaud Penzias and Robert Wilson were testing a very sensitive radio antenna. They kept picking up a faint hiss of radio noise coming from every direction in the sky. They thought it was interference. They even cleaned pigeon droppings off their equipment, thinking that might be the problem. But the noise remained. It was coming from space itself. What they had discovered was the afterglow of the Big Bang. We call it the cosmic microwave background radiation. Here's what happened. In the early universe, everything was so hot that atoms couldn't form. electrons and nuclei flew around freely. Light couldn't travel very far before hitting an electron and bouncing away. The universe was opaque, like being inside a cloud, but as the universe expanded, it cooled. About 380,000 years after the Big Bang, temperatures dropped enough for electrons to combine with nuclei and form atoms. Suddenly, light could travel freely. The universe became transparent. That light has been traveling through space ever since, but remember, space is expanding. As light travels through expanding space, its wavelength gets stretched. Light that started out as visible light has been stretched into microwave radiation. That's what Penzias and Wilson detected. The faint glow of the universe when it was 380,000 years old, stretched and cooled by billions of years of expansion. This is powerful evidence. It's like finding a baby picture of the universe. We can study this radiation in incredible detail. We've built satellites to map it, and what we find is remarkable. The radiation is almost perfectly uniform in all directions, almost, but not quite. There are tiny variations in temperature. One patch is a millionth of a degree warmer than another. These tiny ripples are the seeds of everything we see today. Regions that were slightly denser attracted more matter. They grew into the galaxies and clusters of galaxies we see now. We can trace our entire cosmic family tree back to those microscopic variations, but now comes the uncomfortable part. What happened before the Big Bang? This is where people get frustrated with physicists because we don't have a good answer. Some say the question doesn't make sense. Time itself began with the Big Bang. Asking what came before is like asking what's south of the South Pole. Others say maybe there was something before. Maybe our universe emerged from something else. Maybe it's part of a larger structure we can't see yet. The problem is that as we go back toward the very beginning, our physics breaks down. General relativity, Einstein's theory of gravity, describes the expanding universe beautifully. But when you run it backward to the very start, it predicts a singularity, a point of infinite density and temperature where the equations stop making sense. It's the same problem we have with black holes. The theory gives us infinity, which is nature's way of saying our calculator is broken. To understand the first moments, we need a theory that combines gravity with quantum mechanics. We need quantum gravity, and we don't have that yet. But we can still figure out a lot. We can calculate what happened when the universe was 1 second old. At that point, it was about 10 billion degrees. Hot enough that protons and neutrons hadn't formed yet, just quarks and gluons flying around in a cosmic soup. As it expanded and cooled, quarks combined into protons and neutrons. A few minutes later, some of those protons and neutrons fused together to form the first atomic nuclei. Mostly hydrogen, some helium, tiny amounts of lithium. This is called Big Bang nucleosynthesis, and here's the amazing part. We can calculate exactly how much of each element should have formed based on the temperature and density. Then we can look at the universe today and measure how much hydrogen and helium actually exists. The numbers match perfectly. This is astonishing. We're predicting the recipe of the universe using physics from the first few minutes of cosmic history. And it works, so we have 3 independent pieces of evidence. The expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements, they all point to the same conclusion. The universe started hot, dense, and small, and has been expanding and cooling ever since. But let me tell you what troubles me about this. It troubles me because it raises more questions than it answers. Why did the universe start expanding in the first place? Why was it hot? Why was there anything at all rather than nothing? And here's something really strange. The universe appears to be remarkably fine-tuned. Let me explain what I mean. The laws of physics contain certain numbers, certain constants, the strength of gravity, the mass of an electron, the speed of light. These numbers seem arbitrary. We measure them, but we don't know why they have the values they do. But here's the thing. If you changed any of these numbers by even a tiny amount, the universe would be completely different. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars wouldn't form at all. If the nuclear forces were different, atoms couldn't exist. The fact that everything is balanced just right for complexity, for stars, for planets, for life, seems either incredibly lucky or incredibly suspicious. Some physicists say this is evidence of design. Some cosmic intelligence set the dials just right. Others say it's the anthropic principle. Of course, we find ourselves in a universe that allows our existence. If the universe were different, we wouldn't be here to wonder about it. Still, others propose the multiverse. Maybe there are countless universes with different laws and constants. We happen to live in one of the rare ones that permits our existence. Personally, I don't know. None of these explanations satisfy me completely. But they're the best we have right now. Let me tell you about another mystery, dark matter and dark energy. When we add up all the visible matter in the universe, all the stars, all the gas, all the galaxies, we only account for about 5% of what's actually there. Another 25% is something called dark matter. It doesn't emit light. We can't see it directly. But we know it's there because of its gravitational effects. Galaxies rotate too fast, they should fly apart based on the visible matter alone. Something invisible is holding them together, and the remaining 70%. That's dark energy, something even more mysterious. It's causing the expansion of the universe to accelerate. Not just expand, but expand faster and faster. We discovered this in the late 1990s by studying distant supernovae. It was completely unexpected. We thought gravity should be slowing down the expansion. Instead, something is pushing it to speed up. We call it dark energy because we have no idea what it is. It's the biggest mystery in cosmology right now. So, when we talk about the Big Bang, we're really describing the evolution of a universe we barely understand. 95% of it is invisible to us. We're like ancient mapmakers drawing the coastlines without knowing what lies inland, but here's what fascinates me. Despite all this uncertainty, we can still trace the history of the universe with remarkable precision. We know that 13.8 billion years ago, the universe was hot and dense. We know it expanded and cooled. We know when the first atoms formed, when the first stars ignited, when the first galaxies assembled. We have baby pictures, we have teenage photos. We can watch the universe grow up, and the tools we use are beautiful. We use the speed of light as a time machine. Light takes time to travel. When you look at a distant galaxy, you're seeing it as it was when the light left it, not as it is today. The farther away we look, the further back in time we see. The most distant galaxies we can observe are from when the universe was only a few 100 million years old. We're literally watching cosmic history unfold. But we can't see all the way back to the Big Bang itself. The cosmic microwave background is a wall. Before that moment when atoms formed, the universe was opaque. Light couldn't travel freely. It's like trying to see through a fog. We can't use light to probe earlier times. But we might be able to use something else, gravitational waves. Ripples in spacetime itself caused by violent events like colliding black holes. Some theories predict that the Big Bang should have produced gravitational waves. If we can detect them, we might be able to see even further back, perhaps to the first fraction of a second. This brings me to inflation, a bold idea proposed in the 1980s. The standard Big Bang theory has some puzzles. Why is the universe so uniform? Why does the cosmic microwave background look almost the same in all directions? Regions on opposite sides of the sky were never close enough to exchange information, yet they have the same temperature. How did they know to match? Inflation solves this. It proposes that in the first tiny fraction of a second, the universe expanded exponentially fast, much faster than the speed of light. This doesn't violate relativity because space itself was expanding, not matter moving through space. During this brief moment, a region smaller than an atom inflated to the size of a grapefruit or larger. This stretched out any irregularities, making the universe smooth and uniform. Then inflation ended and the normal Big Bang expansion took over. It's a strange idea, but it explains a lot. And it makes predictions we can test by studying the patterns in the cosmic microwave background. So far, the observations match the predictions remarkably well, but inflation raises its own questions. What caused it? What stopped it? And here's a wild thought. If inflation happened once, maybe it's still happening elsewhere. Maybe it never completely stops. Maybe it creates new regions of space that become their own universes. This is one version of the multiverse idea, an eternal process of cosmic budding. It's speculative. We may never be able to test it. But it shows how far our thinking has come. Now let me return to the question I started with. Where did all this come from? The honest answer is we don't know. The Big Bang tells us how the universe evolved from a hot, dense state. But it doesn't tell us why there was a hot, dense state to begin with. Some physicists have proposed that the universe could arise from nothing through quantum mechanics. Empty space, the vacuum, is not truly empty. It seethes with quantum fluctuations. Particles pop in and out of existence constantly. Maybe the entire universe is just a very large quantum fluctuation. A cosmic accident. Others argue that nothing is unstable. That something is more natural than nothing. That the laws of physics themselves might make a universe inevitable. These are deep philosophical waters. They're at the boundary between physics and metaphysics. But here's what I can tell you with confidence. Whatever happened, it wasn't magic. It followed rules. The universe has structure. It has patterns. It obeys mathematics. Our job as scientists is to figure out what those rules are. We're making progress. A century ago, we didn't even know there were other galaxies. We thought the Milky Way was the entire universe. Now we know there are hundreds of billions of galaxies, each with hundreds of billions of stars. We've measured the age of the universe. We've mapped its structure. We've traced its history back to when it was less than a second old. This is extraordinary. Think about what we've done. Using physics, using mathematics, using telescopes and satellites, we've reconstructed the biography of existence itself. But the story isn't finished. We're still missing crucial chapters. We don't know what dark matter is. We don't know what dark energy is. We don't know how to unify gravity and quantum mechanics. We don't know if the Big Bang was truly the beginning or just a transition from something earlier. These are not small questions, they're the biggest questions we can ask. And the fact that we don't have answers yet should excite you, not disappoint you. It means there's still work to do. There are still mysteries to solve. When I look at the cosmic microwave background, I don't see a solved problem. I see an invitation. Every tiny ripple in that ancient light is a clue. Every galaxy is a piece of evidence. Every equation is a tool. We're detectives investigating a crime scene that's 13.8 billion years old. And we're getting close, so the next time someone tells you the Big Bang was an explosion, correct them. Tell them it was the beginning of expansion. Tell them it was space itself unfurling from an incredibly hot, incredibly dense state. Tell them we have baby pictures in the form of ancient light. Tell them we can calculate what happened in the first 3 minutes. And then tell them we still don't know why it happened at all, because that's the truth. That's the beautiful, frustrating, magnificent truth. The universe started, we're here. And we're trying to figure out how and why. Thank you.